Hello friends, welcome to Bindu Dhadwal chemistry lessons. The topic that we do today is ionization energy in D block elements. So here's the data of the first transition series of D block elements this graph shows the variation of first ionization enthalpy of all the three transition series. The first, that is 3D, 4D and 5D. You can see that the 5D transition series, hafnium tantalum, has higher first ionization enthalpy value than the first and second transition series. This is contrary to normal behavior where the elements placed lower have lower ionization enthalpy values. Now this is because in the 5D series there are 4f orbitals which are fully filled, which cause very poor shielding effect, and because of that there is a greater effective nuclear charge which holds the outer electron strongly, so the first ionization enthalpy value is high. So the first ionization enthalpies of D block elements lies between S block and P block elements. They are higher than those of S block elements and lesser than those of P block elements. The ionization enthalpy generally increases as we move along the period from left to right. There are some irregularities. The increase in ionization enthalpy is because of increase in atomic number, because of which the nuclear charge increases and size decreases, making the removal of outer electron difficult. So the ionization enthalpy value increases. Titanium has ionization enthalpy, first ionization enthalpy value higher than that of scandium, but this value decreases when it comes to vanadium. Now the irregular trend in the first ionization enthalpy of 3D metals is due to the fact that removal of electron alters the relative energy of 4s and 3D orbitals. There is a reorganization energy accompanying ionization. This results into release of exchange energy, which increases as the number of electrons increase in the d-n configuration, and also from the transference of s electrons into d orbitals. For example, for vanadium, which is 23, the electron configuration is argon 18, 4s2 and 3d3. Now removal of this one electron will result in 3d3 4s1. This electron 4s1 electron will also get transferred to 3d, so there are 4 electrons now. There will be more exchanges, and as a result there will be more exchange energy that is released, which will compensate for the ionization enthalpy, and the ionization enthalpy value decreases. Titanium to vanadium. Chromium has low first ionization enthalpy because loss of one electron gives stable configuration of 3d5. So zinc has very high ionization enthalpy because electron has to be removed from the stable 3d10 4s2 configuration, so its value is high. The difference in ionization enthalpy between any two successive D block elements is very much less than the difference in case of successive S block or P block elements. This is because in the D block elements, the electron enters the penultimate n-1 3D shell. This entry into D subshell results in shielding effect, which counters the effect of increased nuclear charge. So increase in nuclear charge is countered by the screening effect caused by the entry into 3D electron or the 3D electron. So as a result, the variation is less. Due to counter effect, little variation is seen on moving along a period of D block. The first ionization enthalpy of zinc, cadmium and mercury are very high due to fully filled N-1 D10 NS2 configuration. You can see for zinc this value is 906, whereas other elements were having value up to 745. Although second and third ionization enthalpies also in general increase a longer period, but magnitude of increase for successive elements is much higher. There are a few exceptions during this journey. For example, there is a fall in second ionization enthalpy from chromium to manganese. So these are the values for second ionization enthalpy. Chromium has 1592 and for manganese this value falls to 1509. This is because the chromium, whose electronic configuration is 3d5 4s1, when it loses its first electron, for the configuration becomes stable 3d5, so second electron is lost with difficulty. It does not want to lose its stable configuration. But in case of manganese, after the loss of second electron, the configuration will become stable, so it's very easily lost 3d5. So that's why the ionization enthalpy value second is lower for manganese. Copper to zinc also, copper has configuration 3d10 4s1. So first electron is lost, but for the second one it has to be taken out from a stable configuration, which is difficult, so its value is high, whereas for zinc it's low. So there is a fall in second from 1958 to 1734. Third ionization enthalpy value for manganese is very high, because configuration for manganese, third, manganese is 3d5 4s2. 2 electrons are lost, resulting in stable configuration, so this electron will be lost with difficulty, so high ionization enthalpy value. Third ionization enthalpy value is high. The third ionization enthalpy value for change from Fe2 plus to Fe3 plus is very small, because loss of third electron results in stable 3d5 configuration. This is for iron. 2 electrons are lost from 4s, third is lost from 3d6, so the configuration becomes stable 3d5, so value is low. So our third ionization enthalpy value for iron is very, very less than third ionization enthalpy value for manganese. The high values of third ionization enthalpy of copper, nickel, zinc explain why they show a maximum oxidation state of +2. Copper, the first ionization enthalpy of 5d elements are higher as compared to those of 3d and 4d because of weak shielding of nucleus by 4f electrons in 5d elements, resulting in greater effective nuclear charge acting on outer valence electron. We have already covered this. And another thing, the ionization enthalpy of 3d and 4d metals are irregular, sometimes decreasing then increasing, but for 5d it's regular increase. So this is about ionization enthalpy.